So how many of you know what contract theory is? Yeah, it's pretty small, even in this audience. Yeah. So one of the things I want to do is introduce you to it. It's a great way of thinking, and there's some nice mathematics, and I want to link that up to the kind of things we've been concerned about with online algorithms and so on. All right, so before I get there, since I have, I guess, a full, or roughly an hour, I do want to step back and sort of say a little bit about why are we doing all of this. You know, most of us are kind of mathematically inclined and we like to solve problems. But in this era, you know, what we're doing is having a big impact. And people are talking about AI and so on, and billions of dollars and so on. So it's kind of nice to think about why are we doing this, and what is the goal? I don't like to talk about AI much. I'm not an AI person. I never said I was an AI person. I was kind of a statistician and maybe computer scientist working on interesting algorithms. But you know, back in the background was always AI. And only in the last 3 or 4 years as people started to use that term again. It was kind of surprising to me. It was machine learning for 30 years. Anyway, if you go back, you know, there was this perspective which is somehow now come back to the fore. And that was John McCarthy saying we want to put thought in a computer, make computers think like humans. And that's an interesting aspiration philosophically. What does it mean? And you know, leads to interesting questions. It's not really what's happened. There's not really thought in a computer clearly, and it's not really clear why. What the goal is an engineering goal. You know, if you took out a human and put in a computer, and the computer was smarter, you know, why should that be better for the world? Maybe it is, but it's just not clear to me. So I want to think more about the systems level. You know, when you build a system, you think about the whole level. You don't think about the individual node and make it super intelligent. You think about the system. For people here, that's obvious. For most of the AI world, it doesn't seem to be obvious at all. They think that making the node super intelligent is the goal. Okay, so an obvious counterpoint to this is that whatever you mean by intelligence, and I don't think we really know what intelligence is. And it's not clear we should know. We may be learning, we know a little bit about what it is. It's almost more of a definition, but intelligence, I don't think so. But in any case, it's not just about the intelligence of a single entity, a human, or an animal. Collectives can be intelligent in ways that the individual are not. Okay, and that's kind of obvious, maybe the people in this room, if you had some economics, you know that a market can have intelligence. It can react, it can be adaptive, it can work at scales, it can work for long periods of time. Sort of all the kind of things that our current AI systems don't do very well, okay? And so the algorithms inside of economics that make these markets work, we kind of have some rough idea what they are. We have microeconomics, but that's very rough. It's based on a lot of assumptions and a lot of kind of previous generation thinking, no data flows, no networks, and so on. So it's outdated microeconomics, okay? And so that's the big opportunity for the people in this room is update microeconomics to the modern world. All right, now there have been people doing this. In fact, some of the networking people, I see Laurent here is a good example, you know, have been building networks thinking about these kind of issues. What's the intelligence of the network? And that's I think, pointing the way to the future. And you know, people that do biology, you know, think about ants. They can build structures without each individual ant knowing very much at all. Okay, so that's kind of obvious. But outside of a few examples like that, we don't have a real dialogue of thinking about collectives being intelligent. We don't have lots of other great examples. And I think in 50 years, we'll have lots of great examples. That's one of the things that's going to happen in the next few years. More democratic mechanisms, more allocation mechanisms, more ways for people and machines to interact. It'll be actually interesting. And I think this is way more interesting than thinking about superintelligence and existential risk and all this kind of crap. Oh, it's being videotaped. Sorry, I take back that last word. Not really. Okay, so let's think about building nice, healthy collectives that use all of the data and use inference and use incentive structures. And let's think about what new collectives could come that could somehow make human life better. That's the goal. Okay, so I've said this already. And again, I think of this as an emerging engineering field. I don't really think of it as a science. We're not really understanding intelligence at this point. You know, someday, yes, slowly but surely. We don't understand it yet. So we're building systems with kind of rough algorithmic and statistical principles and a little bit of economics thrown in there. It's very ad hoc and very rough. There's nothing wrong with that, but we should at least think about the overall engineering goals, at least, even if we don't think about we have the best ideas in the world. And these old aspirations of AI, I really think are warping the whole dialogue And I think you probably all, many of you may agree, but it's certainly there. If you ask a machine learning person, don't you think about collectives at all? Or don't you just think about gradient descent? Really, it's more the latter. That's all they think about is gradient descent. But if they have to push come to shove, they will point to the federated learning paradigm. Okay, federated learning is where you have a central server and you have a lot of edge devices and you're trying to bring as much data from the edge devices as possible in some sense while protecting privacy. So that's the usual constraint that makes it a little different than classical machine learning. You protect privacy. And it's differential privacy. It's not a bad concept, but it's still pretty limited. The overall engineering goal here is just to build a central model, really. And heterogeneity among the user's devices is viewed as a problem. Okay, as an economics kind of person, it's not a problem. That's the whole point, is that there's heterogeneity. Anyway, I want to bash it. I was just at a conference on it, but it was lots of no discussion about agency at the edge. It was all discussion about the data sources at the edge. And how do you get them, and how does Google centrally grab all this stuff, make some promises of privacy, but grab all this stuff and use it how they want to, and make their own business model and so on. So I personally think that's not a good overall engineering goal. It's one, but it's not the best. And I think we can think of better ones as an academic and community. All right, so the first step is just to recognize that at the edge, they're not just data sources, they're people. And people have agency. And there might be computers there too, I don't care, but there's entities that have agency, meaning they care about the outcome. They have a utility function. And we need to know a little bit about that utility and respect it and maybe query it and work with it. Okay, so in particular, if they're mainly viewed as a source of data, let's not use that word data too simply. Data can be a song I wrote on my cell phone, or maybe a novel that Flaubert wrote. He would probably write it on his cell phone nowadays. And that's not just data. If you just turn that into bits, you're really damaged something. Okay, so it's something valued by humans. It has a value. And that value might be determined in a market. All right, and so let's reveal that market. What is that market, and how could people interact with it? So there should be cost benefits at all levels. All right, so again, for these people in this room, hopefully it's all obvious to you, there should be a blend of microeconomics and learning. Okay, and I think for a lot of people outside of this room, though, that's kind of an aha experience. That's, really? I never thought those two should come together. Anyway, you have mechanisms in microeconomics. They should be learning aware. Most mechanisms you look at in classical textbooks are not learning aware. When they use the word learning, they don't really mean our kind of learning. There's not lots of data and updates. In fact, when they say Bayesian, like Bayes-Nash equilibrium, they don't mean statistical Bayesianism. They don't have an update of a posterior. They just have a prior. Okay, and they take averages with respect to that prior. Okay, that's not Bayesian. That's just probabilistic. Okay, and it's a limited form. There's no inference there. All right, so we want to make learning aware mechanisms, and then on the other side, learning algorithms are not mechanism aware. They're just doing their thing, and maybe that's good. Maybe some learning algorithms just kind of behave nicely in game theoretic contexts, but not necessarily, and we ought to be studying that kind of thing. All right, so. I'd also like to give this example of, why am I doing this? Here's an example of a company I'm involved with for 5 years now. It's called United Masters. Steve Stout is the CEO. He's a legendary hip hop producer. And it's created now a thriving three-way market for young musicians mostly. Most music made nowadays is by kids between 16 and 22 years old. Most songs being listened to are by them. It's kind of amazing. It's not the old, rich record company things that are making all the music. But they're not part of a market. They're not getting money for what they're doing. And so it's in some sense completely broken. They do it for a few years and then they have to quit and find some other job. United Masters makes a three-way market. If you're a musician, you sign on with United Masters and you upload your songs and they're mastered and produced by United Masters and then they're streamed out there. There are also brands involved, like the National Basketball Association gets all their music now from United Masters. When they do, and now the third part of the leg is you as a listener, you click on an NBA video and you hear music that's a United Masters artist and they're paid in that moment. Okay, the artist is paid. Moreover, now the brands can start other brands, not just NBA, there's I think 200 brands now. They can watch this process and they can say, oh, I see that musician is liked by this demographic. I like that demographic too. Let's sign that musician to write some more songs. And that is happening right in this moment. And there are 3 million musicians signed on to the United Masters platform. So it's a fight, to fight off the record companies and to fight off Spotify and Google, who just want to grab musicians' data and make money off of it themselves. But it's a good fight. And now what is underneath this? Market mechanisms and learning, critically. If you didn't have that thinking going on, this whole thing would not work. All right, so, and then lastly, why did I get into all of this? Really, my path was recommendation systems. I've always long been interested in them. They're not just prediction systems, they're prediction systems with people. And I found that really interesting. And they've had as big an impact on the economy as any of this last wave of deep learning, just to say. I mean, they really had a big impact. And as soon as you start to think of them getting deployed in the real world, though, you start to see there's places where they're just going to break, and break in simple and dumb ways. And so, they can recommend the same item to many people. And in the case of books and movies, that's not a problem. If you recommend the same movie to, a million people, which I'm sure happens every day at, Netflix or whatever, you just copy the bits. There's no scarcity in the world of bits. Okay, and same with books. You copy the bits, and Amazon can send the same thing. But if you recommend the same restaurant to everyone, you cannot copy the restaurant. All right, and so you create congestion. So again, for this group of people, I'm sure it's obvious, but for a lot of people who took recommendation off the shelf as a commodity and built a company to make all kinds of other recommendations, oops, they caused troubles, and they should have known. And the other example is kind of streets. If you recommend streets to drivers, you're going to create congestion. All right, so we can and should work on this. So the first project I got involved in was, I was doing this. We're trying to create a two-way market. I think really three-way markets are the more thriving entity. But between least, let's have a market between producers and consumers. And we should have recommendation systems on both sides. So that's different from just a classical, matching market. I want matching markets that'll work at scales of, 100 million by 100 million. All right, and so if I go into a matching market like in Shanghai, I'm in there for the first time, I'm gonna go to a restaurant, and there's now 100,000 other people that wanna go to a restaurant that night. That's a matching problem. And you're not gonna know my preferences and utilities a priori. I don't know them. I wanna sample some restaurants, okay? And the only way I'm gonna do that in an efficient way is to take, Vianney has already been there, and Vianney are linked in some kind of a graph, then whatever experience he has should bleed over to me, and that should be my warm start. Okay, so this is a model that I think makes a lot of sense, and Uber did this to some degree. Uber is a matching market, and Uber matches drivers to riders, and one can argue with it. I tend to think Uber was a success. Now they're having to reprice things and all that, and whether they'll succeed as a company, I don't know or care. But it was a living, thriving matching market. But it wasn't really a recommendation system on both sides. Okay, and that's what I think part of the story has to be. So we want to learn preferences in the context of other preference learners. Okay, so anyway, if you believe all this stuff, which everyone in this room does, then you start turning to what problems can we work on as academics. All right, and so I kind of came late to this game. Here's the ones I've been working on for the last 10 years, but people like Vianney and many others, we're ahead and working on this kind of stuff long before. And now it's kind of fun to learn what they've done after all these years. One of the things I've done is maybe a little different from the ML or econ CS kind of axis is relationships between optima, equilibrium, and dynamics. And I'm not going to talk about that today. That's a whole separate talk. But we got really good in the last 10 years at understanding how to find optima in high dimensions, even if they're saddle points. Okay? We can go to saddle points, and I can tell you the dimension dependence on various algorithms. I give you upper bounds and lower bounds, and those match up to logarithm factor, and it will do stochastic and as a function of dimensionality. We don't hide dimensionality. We can actually give you dimensionality. It's polylogarithmic in dimensionality. So just a huge progress there, kind of building on Nesterov, Nemirovsky, but taking that quite a bit further. And in some sense, that's kind of done. And now we want to turn to equilibria, because real life systems don't find optima, they find equilibria, maybe. And what algorithms find equilibria? Well, the gradient-based algorithms, as probably all of you know, mostly fail if you look at trying to find general equilibria. They don't find fixed points. Okay, they can spiral out when you have a fixed point. And so now take but anyway, there are algorithms like extra gradient that will find fixed points. So take all the progress we made with gradient-based algorithms and apply them to extra gradient, and that is starting, that's or ongoing. Okay, that's an open, high-dimensional extra gradient with saddle points and stochastics. Okay, there are definitely people working on that. But of course, it's not just about equilibria; it's about dynamics. And moving equilibria in the real world, it's not going to be one fixed equilibrium. It will move for various reasons, and we want to have algorithms that track that well and are effective in that sense. More like a control theory thing. Anyway, that's what I've mostly worked on the last 10 years, but I've really gotten interested in incentives and uncertainty quantification, and most of my work the last few years is all about that. And so I'm going to pick a couple of projects that get into that. A little bit of exploration, exploitation issues, but mostly the information asymmetry issue, because that to me is really what's interesting and somehow a little bit missing. It has to do with contract theory. When people talk about incentives, often they mean auctions, and auctions are great, but auctions have some limitations that I want to discuss a little bit, and I think contract theory is an appealing, flexible way to think. And then I'll talk a little bit on uncertainty quantification, because that really is a nice phrase. In statistics and machine learning, it's kind of been limited. Uncertainty quantification means an error bar. Okay, and to me that's fine, and it should be a real error bar. It should really cover the truth, but also it should kind of take into account all of the uncertainty. They rarely do. But also, if you take an economics point of view, uncertainty is not just an error bar. It's not something you could reduce by multiple IID sampling. Uncertainty is that someone out there knows something I don't know, and they're not going to tell me that. Okay, that's an information asymmetry, and that's fundamental and structural, and I got to put that together with my usual UQ ideas. Okay, so hopefully that was an interesting introduction to you. That was maybe a 15-minute long introduction, but hope it was worthwhile. So this was a first project with Lydia and Horia that we did at Berkeley when I kind of came back saying I want to work on incentive structures and matchings and so on. So this little project was just kind of put the two together, and so I'll go quickly. It's in this audience, I think it's probably of less interest because everyone's done things like this. But just to say, this was an attempt to do kind of this restaurant problem. I go into Shanghai and I got to try out restaurants. So how do I do it? Well, I do a bandit algorithm. All right, so I'm doing a bandit algorithm, and you all know what bandit algorithm is for other people, but you could find, for example, upper confidence bounds and then get logarithmic regret in these bandit algorithms. All of you know that. So that's on the learning side, and then on the economic side, we're going to have a classical matching market. And there, classically at least, you needed to know the preferences of the buyers for sellers and the preferences of the sellers for buyers. And then you ran an algorithm that had a stability criterion and blah, blah, blah. Beautiful literature. And so now you want to merge these two ideas. You say, well, what if this matching market is in a domain where I've got vast numbers, just tens of thousands of buyers and sellers. There's no way I'm going to write down a preference sorting on them a priori. And so how can you use these ideas and at that kind of scale? Well, you need some kind of a recommendation systems on both sides, and you need exploration, exploitation all mixed in. And I think that we're not there yet, really. I mean, the recommendation side part of it, I don't think we're there. But anyway, putting together the two, you can get sort of, a natural model, which is where you have multiple agents that are trying to explore and exploit. And here our model was a congestion model where if both of the agents picked the same arm, only one of the agents got a reward and the other got no reward. Okay, so that's one model. The classical congestion markets or congestion channels in networks was a little different. If two people hit the same channel, neither of them got a reward because they both, they screwed up the channel. This is different, it's more of an economic model where one of them gets it. Who gets it? Well, the other side of the market chooses, because the other side of the market also has agency. So the restaurant decides I'm going to let that person in and not that person. There's an allocation. So, and that may be learned as well as part of this. Okay. Okay. So under that kind of model, you can now do the mathematics, and you can write down a notion of a bandit market where you have exploration, exploitation in the context of a market, and we're focusing on still getting good regret, even though I'm competing. Okay, so now think about it for a moment. If I am the human there and I pick arm 2 because I seem to like it, my UCB interval says arm 2 is looking pretty good, and I pick it, and the bear seems to pick it too fairly often, and when the bear picks it, the bear wins because seemingly arm 2 prefers the bear to me. I learned that, and now I've got to explore some of the other arms more than I otherwise would. All right, when I explore the other arms more than I otherwise, that's regret. That will cost me. And so I need to quantify that regret. And the question is, so that's now, how does regret scale with competition? That's the interesting question. All right, and so in this particular model, we were able to figure that out. And I think I'll just show you the equation there. Here's the equation. So the regret for the ith agent scales in the usual way with the number of arms and the number of agents. and logarithmically in the time horizon. So there's no cost for having competition, except there's a constant term, and that constant term is in the denominator. It's a gap, and so it's a gap between the rewards for the different agents. If I share reward distribution with Vianney, and that means he'll like ARM2, I'll like ARM2, that means there'll be more competition, and that number will be small, and that'll make the regret go up. So the regret goes up by a constant that depends on the competition. Okay. Anyway, so that was our result. Now, there are a couple things I didn't particularly, I thought this was a nice first step for at least me and my group to get our feet wet, but there are a couple things I didn't like, and one of them was there was no transfers, and I kind of, when I look at real matching markets, like restaurants and all, I see transfers, and I wanted to think about that. And secondly, it was kind of ad hoc dynamics. You threw in a learning algorithm like UCB, and you analyzed it. And I'm more of a control theorist. I want to throw down a Lyapunov function and kind of derive algorithms from that. All right, so this second project followed up on this is with Mina, Alex, Yishin, and Jacob, where we're looking at matching markets with transfers. And I just want to briefly tell you the result here. Just to say what we're trying to do is we're introducing the Shapley-Shubik model instead of the not transfer, the money-free model. And we'd like to actually find a way to figure out what should be the transfers. So we add the prices into the overall dynamics. And we'd like to get a Lyapunov function that tells you how to get something, okay? Now, what something are we aiming for? All right, in classical economics, it's often stability, okay? You're stable or you're not, all right? And again, with my control theory background, I feel that that's great, but you need a quantitative notion of stability. You're either stable, you're a little bit unstable, or you're really quite unstable. And then that gives you a Lyapunov function, perhaps a way to improve. Okay, and so just stable or not is not enough. You've got to make that more quantitative. And so that's what we did in this project. And I'm just going to write that up there, and I don't want to spend time on it. But this is kind of our Lyapunov function. It's a function of the matching and the prices. The prices are the tau, the transfers. And it has kind of a, there's a maximum or subsets, so it looks like a Shapley value kind of thing, and it looks kind of economic. What you can do is you can take the dual of this problem, and you can show that the dual, maximizing the dual, is obtained. It measures the amount of extra money from an external agent would have to put into the system to go from stability from instability to stability. Okay, so that has a natural economic interpretation. Okay, so this function is well defined economically, and now it is continuous, and you can prove things with it. Okay, so now we go back to the previous project, and we say, can we prove that thing has logarithmic regret? There we just did it by 3 pages of messy calculations. Here we can just take the Lyapunov function, write it down, and we immediately get the logarithmic regret. Okay, so I'd encourage those of you who are working on learning meets matching markets to consider this Lyapunov function. Okay, so that's that. Okay, so that was the first part. All right, and so the other thing that I wanted to spend the next part of my research life on was incentives. And so this is a recent effort for the last year. Many colleagues at Berkeley. Navasini, who's here, I see her in the audience, is one of the colleagues that she will be talking about incentive and contracts and so on, and there's several others. Anyway, this project, this paper was with Stephen, Michael, and Jake at Berkeley. Let me just say a little bit about contract theory. A third of you seem to know about it. One way to think about it is that you've got game theory and you've got inverse game theory, aka mechanism design. Okay? In game theory, one way to conceive of it is it's just like physics. You're just trying to write down some laws and use those laws to predict behavior that you might see in the world. And you go out to a particular real world situation and you see behavior like that, you say, oh, my model must be good. So it's just like Newton's laws, F equals ma, I write them down, I derive some consequences, and I go off and see if things fall according to the equations, the ODE that I derived. All right, so that's the forward direction. And now you got to define kind of what are your laws, and there are things like the equilibria, the Nash equilibria or the Stackelberg or the various equilibria. And as you know, there's a lot of debate about whether there's been success in really explaining behavioral phenomena. I would say mostly yes, but there's definitely some failures. And the engineering mindset says the other direction. And so it's just like taking physics and now I want to do mechanical engineering. I'd like the bridge to stand up, that's my goal, and I go backwards to find out what structural ingredients I need to make sure the bridge stands up. And in economics, going backwards is called mechanism design. And now you got to decide what is my goal. First of all, I got to say what equilibrium and what class of games. And so if you start with the Nash equilibrium or Bayes-Nash, you have a sort of a symmetric situation. There are many players like an auction. They all come in, they may or may not know something about each other, but it's symmetric. And they play and there's an outcome. And if I want to achieve a desired outcome, fairness or revenue, I can go backwards and find a good game that will do that. Okay? So that's an auction. That's what an auction does. If you say, no, I prefer these sequential games, more like Stackelberg equilibria, where there's a leader and a follower, that's the game that I think models my situation better, then you can say, what if I try to invert a Stackelberg game? What is that? Well, it's not an auction anymore, it's a contract. It's a contract theory. Okay, so that's what contract theory is. It's kind of the inverse of Stackelberg. And you all know what they are. This was famous. They really hit the scene in economics in the 80s. The airlines were failing. Air France and Alitalia and all this were failing. Why were they failing? Well, partly because they were offering one price for the entire airline. Just like in a movie theater, it's one price for every seat. Even that's changed now. It used to be one price for every seat. And that's what the airlines were doing. And as you can imagine, it's very hard to set that price. If you set it too high, you get a few people on the airline, it's mostly empty. If you set it too low, you get the airplane full, but you make no money. Okay? And so they were setting their prices in some way, and then these low-cost airlines came in and said, your airlines are empty because you're setting this price so high. We're going to fill our airlines really cheaply, and we'll make a little bit of margin, and we'll beat you out. And they did for a year. They basically killed off some airlines, and most of the airlines looked like they were dead. Famously, American Airlines hired an economist who knew contract theory, who came in and said, what you need is something where it's a mechanism where there's more than one price. You need to have multiple services, and for each service you have a different price. And now you have more freedom, and as you all know, this makes sense. There are people with different willingness to pay for a flight from here to Paris. And it doesn't mean just the rich people pay the more, it's how much you care about going to Paris tomorrow. And so for me to access that willingness to pay, I will offer a fairly high price with a higher quality of service. It's called business class nowadays. And it's not really much higher, I can assure you. I've been in business class from here to Paris. It's a little bit bigger seat, and it's a tiny glass of red wine. And unbelievably, people pay hundreds more euros for that. But that's called willingness to pay. Whereas there's lots of other people that look at that offer and they say, no, there's way cheaper here for being on the same airline, and I don't care about the little glass of red wine and the slightly bigger seat. I'm much more happy to get in the back and feel good about myself by saving money. So anyway, there's different kinds of people in the world, and so if you offer not just multiple prices and price discriminate, trying to decide that person can pay more, that person can't. Instead, you offer the same menu of options to everyone, and now you set the terms of the option and the price in a smart way. You can prove theorems that say you'll get high social welfare, high revenue, and so on and so forth. And this is not an auction. You could also auction off the seats in the airline. That would be a Nash equilibrium of people kind of competing with each other to be on the airline. This is an asymmetry of information. The airline, if they knew how much you're willing to pay, they just charge you that. They don't know, that's the asymmetry, so therefore they have to kind of give some options. All right, so anyway, if you haven't read about this and all, I highly encourage, there's a book by Lafont and Martimore that was written in 1970, roughly, and I consider it a beautiful book. It took me 3 times to read it before I could understand it, and it's not because the math is hard. The math is pretty easy. It's just interesting. It's a non-trivial thinking style. So anyway, that book I highly recommend. Okay, so now we're going to try to take that old theory and update it to be including learning, just like we did in the previous project. All right, so learning, or let's call it now statistics. All right, so classical contract theory, in the naive version of it, didn't have any learning or repeated games. You just set a set of options and prices, and then kind of what happens. Ad hoc, someone adjusts the prices a little bit, okay? But if you're a learning person, you say, well, we like to do that in a more rigorous way. Okay, so here's our thought experiment domain. We've been rolling this out in. It's clinical trials. So clinical trials is, first of all, it's hugely important for, it makes medicine work. And it's hugely costly because it's basically A/B testing. So you have a vaccine candidate here in your regulatory agency. You look at the vaccine candidate, you know nothing about it. You have to test it on 15,000 people in each arm and see, how well it works. And you do that at a pretty immense cost. And that happens for all areas of medicine. So here's some numbers, in the right column you can see phase 3 trials, tens of millions of dollars for each area. And so it's, billions really of regulatory cost. So now the question becomes, how do you regulate really in this kind of world, of a data-oriented world? Just pure A/B testing is okay, but boy, it sure is costly and it has some problems. And I'm going to now tell you about those. All right, so just to allude to where I'm going to go, the FDA in the United States, the Federal Drug Administration, is basically a bunch of statisticians. They are trying to keep the false positive rate low and the false negative rate low for drugs to go on the market. That's their goal in life, and they're good at that. But they're not economists, at least their style of thinking is not economics, and so they don't think about the incentives. And I think, well, they do think about it, they're aware of it, these are smart people. But I don't think they're using contract theory to think about it, and I think they should. So if the principle is the FDA, so you just say leader follower, that's language of Stackelberg, but you invert Stackelberg, you get contracts, you say principal agent, just to change the terminology. So principal is the FDA. They only have partial knowledge. They look at a drug candidate, they don't know much about it. Who has the knowledge? Well, some of the knowledge is possessed by the agent. The agent is the pharmaceutical company who knows about that drug candidate a little bit more. They know that protein. They put their engineers on it for years. They studied it. They mutated it. And they know something. Maybe they even did some internal testing. They didn't spend tens of millions of dollars, but they spent a little bit to test it. So they know some things. But they're not going to just transfer that knowledge to the principal. And the principal can't just sample something and learn about what the agent knows. It's a structural asymmetry. The agent has competitive advantage, and they have secrets and blah, blah, blah. They're not going to just give it. And if the principal insists, like a strong regulatory law like we see in the European Union, I can tell you what's going to happen. The agents will lie. Okay? Because the incentives are to make them lie. They'll hire a lot of lawyers and try to lie. Okay, so how should we think about this problem? Well, here, at the top is how the FDA kind of mostly has been thinking about it in the textbooks. This is a null hypothesis testing situation. So at least let's simplify this down. There are bad drugs and good drugs. Bad drug, theta is equal to 0. Doesn't mean you hurt anybody. You screen for that, so the drug won't hurt anybody. But bad drug means it just doesn't help anybody. It's like sugar water. Whereas good drug helps people relative to the current standard of care. And the FDA are good statisticians. They can keep the probability of approval if it's a bad drug below 0.05, that's a false positive rate, and they can keep the power above 0.8. And the numbers are a little more stringent than that, but that's the idea. And if you ask, is this a good protocol? Well, statistically, it's an optimal protocol. It's the Neyman-Pearson test. But it's not a good protocol if you forgot about the incentive structures. So look at case 1. Suppose there's a small profit to be. What does that mean? Well, it costs you $20 million to run the trial. That would be your reservation price. And if you're approved, let's say you make $200 million, so this would be a small little niche drug. And so now the CEO can do the calculation, the expectation of the profit, if counterfactually the drug is not a good drug. Okay, no one knows if theta is equal to 0, but the CEO can imagine a world in which it's not an effective drug that they're sending up to the FDA. And she can calculate with those numbers and find out the expected profit is minus 10 million. Okay, so she goes to all the engineers in the company and says, folks, do not send drugs in unless you're really quite sure they're good. All right, and again, she may not even know herself. There's another principal agent problem inside of that. She's got to make sure her workers really follow this. All right, well, suppose she does that. And so now the workers send in drugs that they know are probably likely to be pretty good. The FDA tests them with a false positive rate of 0.05, and everybody is happy. Good drugs go on the market, and the companies don't lose money. The reality, though, is often more like case 2, 20 million to run the trial, and if you're approved, you might make 2 billion for a year, say. That'd be like ibuprofen or something. And now if you plug in the same numbers, the CEO will realize that even if her drug is not actually good, she will stand to make an expected profit of 80 million. Okay, and just by plugging in those numbers. And what's happening? Well, there's that 0.05 is the false positive rate. If you send in enough drugs, you'll get a few through. Now, is that unethical? Well, yeah, but humans do it. And they do, they will. And it's not unethical in the sense you're hurting people directly. Your drug, you screen for that. You tell yourself a story so you can get to sleep at night about that. The fact is, lots of drugs on the market right now are ineffectual. Okay, that's because of this. Is that killing people? Yeah, it is. Okay, so you shouldn't really sleep at night. But it's the best you can do in the game that you've been given. All right, so let's now think about how to mathematically model this. All right, so just briefly, because I do want to get to one other thing here. Here's a contract design. It's an opt-in protocol that the principal gives to the agent. It says, agent, if you want to play this game, you've got to pay a reservation price R, like 20 million, and then you get to choose a payout function from a menu that I will design. A payout function is terms of a contract. It'd be like, the licensing terms. How long, how far, how many cities can you do it in? Various constraints of all kinds. So there's a list of those things. So it's like business class and economy class. And now there's not a fixed price associated with it. What there is going to be is there's going to be a random variable selected. Okay, and so the way it works is now you do a statistical trial and get an observation from nature that's sampled from P of theta, and that's the true theta there. Because even though neither the principal agent knows theta, nature knows theta. So you sample from nature and you get a sample from the truth. And now you plug in Z to the payout function, and that's the amount of money that the agent will make, F of Z. The utility will pay that out, and their utility will depend on the truth, because even though no one knows it, over time people will realize whether the FDA is doing their job or not. Okay, and so this is set up for really many regulatory situations, okay, not just this FDA one. Okay, agents are going to maximize their payoff, so there's your best response. All right, and now you need to write out some incentive alignment or individual rationality constraints. So let's just say that a menu of options is incentive aligned if for all of the null drugs, when you sample from the distribution P where it's null, so that's from the null hypothesis right there, okay, then the amount of money you make minus the reservation price is less than or equal to 0. If that were strictly positive, the pharmaceutical companies could make money from nothing. And so the FDA will set it up so that doesn't happen. All right, now critically, this is under the null hypothesis. We're not trying to get a notion of power here. We're trying to just make sure that we don't make errors. Okay? All right, so if you define it that way, and we now have a class of functions, can you ensure this? Well, if you do the P less than or equal to 0.05 protocol that we get from statistics, it will not be incentive compatible. Okay, so that's a problem. But are there incentive compatible designs? And the answer is, yeah, there are. And so this theorem down here summarizes our paper. We show that a contract is incentive aligned if and only if all payoff functions are e-values. So what is an e-value? Well, in a simplest version of it, it's just a random variable, so it's a function on the sample space. It's non-negative, and its expectation under the null hypothesis, again, that's really important, is less than or equal to 1. Okay? So you all heard of p-values. P-values are tail probabilities under the null hypothesis, probability being further out than an observed value if the null is true, counterfactually. P-values, as you may know, have some problems. You can't put p-values together easily, and you can't stop trials when a p-value is beyond, smaller than some number. E-values fix that, and they fix that because these are more, in fact, a nice way to see that is the general version of this is non-negative super martingale. Okay? And so since it's a non-negative super martingale, you can do either optional stopping theorems that work, and then you can put two of them together straightforwardly with probability theory. Okay, so in statistics, we like e-values nowadays. They're growing in popularity. And what our theorem has shown is a perhaps surprising connection between these nice measures of evidence in statistics and incentive-compatible contract theory. Okay? Let me just say that that expectation being less than or equal to 1 is kind of shows that X is evidence against the null if X is large. So if you got an X of 5, you say, well, under the null hypothesis, that's very unlikely. I can reject the null hypothesis. That's how it's used in statistics. And here that makes sense in this contract example. Okay, so that's that story. I encourage you to look at our paper. We've got now several follow-up papers on this, kind of trying different levels of uncertainty on the two sides, different kind of asymmetries and all that. And I just wanted to advertise for Navasini back here. She has one of the follow-up papers where the problem is to delegate data collection. So the agents now are actual data collection agents. So let's move out of the FDA example. And the agents need to be incentivized to not only supply their data, like in the federated learning, but also to supply more data, okay? And there are many services out there that are supplying data, and you'd like to ask what should be the incentive structure and what kind of contracts are good ones here. So Navasini, you could talk about that this week, or, okay, if you want to hear about it, grab her. She'll give you the story about, I think I have a slide just sort of summarizing some results. She has studied linear contracts and shows that you get a constant factor multiplicative approximation to the first best scenario. That's where there's no hidden, where there's no asymmetry. And then when you introduce the asymmetry, you can turn that into a convex problem and get an additive error. Okay, so I'll let Navasini go with that. Okay, so last 10 minutes. Let me turn to this last piece of work. This is very recent. It just appeared two weeks ago in a journal. And so this is, again, this is going to be less directly about incentives. I want to now move more to this information asymmetry. Okay, so I'm going to argue that information asymmetry is everywhere. We've been taking this too much of a centralized paradigm for machine learning and not even thinking about it. And so I'm going to suggest it's everywhere. And yes, we have to think about the incentives. That's what I did in the previous part. But now let's just think about the consequences of not taking into account information asymmetry and just think about the uncertainty quantification issues. Okay, so that's what my last little section's on. All right, so this is with Anastasio, Stephen, Clara, and Tiana. I guess some of these people have moved on. So Stephen's now an assistant professor at MIT. Clara is now a scientist at Genentech, and Tiana is a postdoc at Stanford, and Anastasio is still with me at Berkeley. Okay, so we're now in deep learning land. You all have heard of AlphaFold. AlphaFold is at least as important as the large language models. It's a very accurate predictor of protein structure, and so that's changing biology and by extension many sciences. And so I want to dig in a little bit to where's the information in AlphaFold and how does a user access that, and are there asymmetries? All right, so first of all, just to be clear on what the setup is here, the goal here is you take an amino acid sequence, this string, and that string will fold up into a 3D structure, and you like to predict that 3D structure, okay? And so you now need a ground truth to compare to, and it's slowly over 40 years, there's been a growth in the number of crystallized structures where you know the structure. So there are now hundreds of thousands of amino acid sequences whose structures are known. Hundreds of thousands sounds like a lot of data points, but it needs to be way, way, way larger to design new kinds of medicines and so on. Every virus, of which there are gazillions of viruses, especially the macrophage that attack bacteria, those macrophages are important. Each one of them have got their own proteins and so on. So that's not very much data. And now AlphaFold can give you hundreds of millions of predictions that are as good as anything we have, and they have pretty high accuracy. Okay, you do held out tests and so on, it looks really good. So there's a temptation to use the output of AlphaFold to drive science. Let's just take AlphaFold output as data. All right, and so that's happening now all the time, and we see people talk about AI for science. This is often what they mean. And here's an example of this happening. So this is a paper published in 2004. It was a negative result. They were trying to study the importance of intrinsic disorder of a protein for the activation of the protein. So proteins mostly like to fold up into a globular structure, but occasionally there's some strands hanging off of them, and that's kind of because of quantum fluctuations. It doesn't want to stick to everything else. And it used to be thought, I suppose, that those strands were just a problem, that was a bad protein. But then it was slowly started to be realized that when you put multiple of those proteins together, and like in structures, the strands can touch each other and create grid-like structures, and you could put them in membranes and modulate flow. So it turns out to be pretty important, and it's an ongoing issue to study this. Okay, so they said, let's just grab all the proteins in the protein data bank. There were 10,000 in that era, and look for the ones that have intrinsic disorder. do they tend to be phosphorylated, meaning they're active biologically? Okay, so that's now a hypothesis test. And you can do it with a little statistic. They did it with an odds ratio. And now the odds ratio, if it's 1 between phosphorylated and not, the probability of intrinsic disorder, then there's no effect. And if it's bigger than 1, there's an effect. Classical hypothesis test. They did that with their 10,000 data points, and they got the confidence interval. They were statisticians, they're not just predictive machine learners. They got a confidence interval, and sadly, it covered 1. So they couldn't say anything. Even though it looked like it was kind of big, it covered 1. So you had to be honest and say, we can't conclude anything. So now in 2022, someone comes along and says, well, now we have AlphaFold. We don't have to worry about sparsity of data, scarcity of data. So let's take the 200 million AlphaFold predicted structures and use them as data and do exactly the same analysis, do the same odds ratio and calculate a confidence interval and see if we can make a conclusion. And they did, and they made a conclusion that, in fact, there's an effect. And I'm going to show you their error bars here in a second and then see what you think. Just to say this is happening all the time, here are just some titles that we picked out of some recent articles, and you'll see it happening all the time, more and more and more. So is this a problem? Is this kind of, or should we just kind of not worry about it? Okay, well, it is a problem. All right, and here's the issue, that AlphaFold, as good as it is, does make some errors. And the problem is that scientists are mostly interested in situations kind of at the edge of knowledge, all right? If they're studying things that are really well known, for which there are lots of structures, there's no errors there, that's fine, but they're not going to do that. They're going to go out here and study things that are more at the edge of knowledge, and there's not many structures, and there's a chance they'll have a lot of errors. You don't know that a priori, but it is going to happen a lot. And in fact, in AlphaFold's predictions, the one on the left is a prediction, the one on the right is the actual experimental structure. So you see, specifically, it's not doing the intrinsic disorder very well. All right, so if you put all the data from AlphaFold into an odds ratio, then maybe it's going to be problematic, and it is. All right, so great. So this slide is an important one. Let me just spend a moment on it. Here's our odds ratio on that axis. So if it's equal to 1, the probabilities are equal. That says you accept, the null hypothesis is true. If it's bigger than 1, there's an effect. All right, so now doing what I've just said, and you get a confidence interval based on AlphaFold output, you get that little gold region right there. So you can see it's really small confidence interval. That's good. You're very sure of yourself. All right, and why? Well, because you have 200 million data points. So you got a really tiny confidence interval. Okay, so that looks kind of on the face of it pretty good. And of course, it doesn't cover 1. So you can now reject the null hypothesis and say, yeah, there really is an effect. So we did a lot of experiments here. We took the AlphaFold output and all that, and what we did is we took half of the entire database, and we held that out, and we did Monte Carlo on that to get an idea of ground truth. So long experiment. And we treated that ground truth over in the second half and redid their whole experiment on the second half. So the ground truth is the dotted line there. And you can sort of see up to Monte Carlo error that there probably is an effect here. It's bigger than 1, okay? But the gold region does not cover the truth at all. That's a little concerning. It's supposed to be a 95% confidence interval. It's supposed to cover that truth, that thing, 95% of the times. It looks like it's not doing that. Okay, you're still making the correct decision, so maybe who cares, all right? And that might be a typical machine learning reaction. We got enough data, who cares? All right, so you could say, well, no, I'm going to be a careful statistician. I'm going to throw out the AlphaFold. I'm going to go back to the data, the gold standard data. There now are 100,000 data points, not just 10,000. Redo the thing and get the confidence interval. Now you get that gray region. And so you can see the confidence interval is really big, and it covers 1, so you still can't conclude anything 20 years later. All right, so anyway, long story short, we have a new method, which we call prediction-powered inference, that will deliver confidence intervals, kind of combining these two things. Okay, and you can't just naively combine them. You got to do this in a smart way. What we're able to do is produce confidence intervals that will guaranteed to cover the truth, just like a classical confidence interval, but generally are smaller. And now we're not able to prove they're always smaller, and I'll tell you why. You wouldn't expect to be able to do that. But they're often much smaller than the classical confidence interval, so they're getting the best of both worlds. Okay, so I want in the last few minutes here show you how we do that. But before, let me just convince you that this is kind of a real serious thing. First of all, let me set up the problem a little bit. This looks like semi-supervised learning, but it's not, but it's similar. You have some labeled data, meaning there's like sequence and structure, and then you have the AlphaFold predictions for the labeled subset. then you have a vast unlabeled data set where you have the sequence, but you don't have the observed ground truth, and you still have the AlphaFold predictions. From all of that, you would like to produce a CPP alpha, a confidence set which contains the truth with an asserted probability. Okay? Semi-supervised learning is different. It says, I'm going to take all my unlabeled data and use it to improve the predictor I got from the labeled data. Okay? We're not trying to improve the predictor here. That's AlphaFold. We can't improve the predictor. We're trying to take the output of AlphaFold and correct it because we think it's probably biased. But we don't know how it's biased. If we knew how it's biased, we'd have an importance ratio. We just shift it over, but we don't know that. So we're trying to improve it nonetheless. Okay, so just a couple of other examples. This is a gene expression example where you throw a little bit of DNA into a cell and you ask, do you get expression, and try to predict that from the sequence. And you run a computer algorithm or a machine learning algorithm to make those predictions. And again, you can see that the computer algorithm will give out a very narrow confidence interval, but it's not covering the truth. The new green interval is really quite good. It's covering the truth, and it's much smaller than the classical interval. Here's my favorite example. This is just a kind of econometrics problem. You're trying to predict some, logistic regression coefficient based on people's data. And you use a machine learning algorithm, and you get a very, very narrow confidence interval, but you can see it's wildly wrong. It's extremely biased. Okay, and so our new corrected one is the green one there. Again, it does cover the truth, but it's not a big improvement in terms of size. It's a little thinner, but not much. Well, why? Well, because it's using a machine learning system which is not good. All right, so we don't expect to get a big improvement over the classical interval, but we do get some. And at least we're being honest. We still give you back a confidence that we guarantee covers the truth, and it's as big as it is. Okay, so you know. Okay, so here's how we do this, and then I'll finish up. So as a statistician, I tend to think about the world as there's the population, and you sampled from the population, you got some data, you get a statistic, and you talk about the sampling distribution of that statistic. All right, so here, in the population, there is a true theta star. Let's say, for example, it could be just the mean, the expectation of y. And there is the AlphaFold output. If it were to look at the whole population, it'll have some bias. And let's call that theta twiddle of f. So that could be the expectation of AlphaFold. There's a difference. If these are expectations or just means, then that difference would be a classical bias. But in general, it's not a bias. It's just, we call it a rectifier. It would change the predictive models, some functional of the predictive model to be the correct one. All right, now, we don't know that quantity, nor do we know theta twiddle f, nor do we know theta star f, but all of those are parameters in the population. And statisticians know how to take data from the population, sampled, and get a statistic that will inform us about parameters in the population of any kind. So in particular, I could get information about the rectifier. That's what I use my data for, my sample data. All right, so what does that mean? Well, I'm going to get the rectifier as a confidence interval on all the possible rectifications. There is one rectification in real life, but I don't know it, but I can get a confidence interval on all the possible rectifications from just doing concentration inequalities. Okay, now what do is I go back to the original AlphaFold output prediction, and I push it forward with all of the rectifications that are probable given the data. And I get a new confidence set. I'm not correcting a point estimate. I'm getting a new confidence set, which is all of the possible AlphaFold that's corrected with a rectifier. Okay? And now it's a little bit of mathematics to convince yourself that CPP will contain theta star with an asserted probability. And if you're interested in some mathematics, I just kind of wrote it out here. Let's take the case of M estimation, where our parameter is the minimization of an expected loss. The gradient of the loss, let's call that G. And so now everything is expressed in terms of gradients. And the expectation of G is equal to 0 by definition. So you can add and subtract a term. You can get that expectation. You can get the rectifier is now appearing there. And you can get a point estimate of the gold term, and you can get a set estimate of the rectifier. You subtract, and you get out CPP. Okay, so that's kind of the setup, and you can now go to the paper and see this done carefully. There's now been several follow-ups on this. This did appear in Science 2 weeks ago, and that's a whole story of its own. I don't like to put papers in something like that, but I wanted to get out to all the AI for science people, and let me just say it was a fight to get it in there. It's one of these political things that one hates to engage with. Okay, so I'm done. Let me just leave that slide up there. Just return to the arguments I was making earlier. This AI buzzword is dominating our lives. I consider it to be a tragedy that it's come back and that it's kind of warping our field. What is our field then, if it's not Elon Musk and Sam Altman? Well, it's just an engineering field, just like chemical engineering. You started with chemistry and quantum mechanics and developed principles for building factories. You know, new mathematics was needed and care was needed to make sure the factory would work, even though it worked in the lab, it didn't work in the factory. Same thing, electrical engineering, you had Maxwell's equations, and new principles were needed to turn that into communication over the waves and bring electricity into houses without burning them down. That's called electrical engineering. Same thing here. We have little principles of inference and algorithms that'll work in little small problems, and we're trying to then build huge, vast factories like, you know, transportation, healthcare, and so on. And we have no idea really that they'll work, and we need new principles. So that's to me what our effort has been. And I don't care if you call it AI or whatever, but it's totally different from the dialogue that I hear, and I just hope that people will start to resonate to something more sober like this. Thank you. I could repeat the question as you wanted. Yeah.
In the contract theory,
yeah.
to sign the contract, you needed to know F as a function.
Yeah.
So this is the reward
yeah.
the agents get.
Given the noise that, yeah.
And we can, given that information, we can also tune the A/B testing so that the CEO doesn't send bad drugs.
If we tune it too much in our favor, the CEO is going to look at that contract and walk away. It's an opt-in contract.
Yeah, no, sorry. The question is, we have this information F,
yeah.
and we will apply either contract theory or a new A/B testing. So the solution, given F, we know we can tune A/B testing, and we don't need contract theory to solve the problem, the initial problem that the CEO sends bad drugs.
No, I don't understand what you're saying, but what we do is we design this list of Fs, and each F we publish it. The terms are clear. It is now a function. You get to see that whole function, okay? Now you select, given on what you know about the candidates you're sending in, which F to use. That selection process is hidden from the regulatory agency, okay? They just know they're now getting some drugs with certain Fs being selected and some certain prices being selected. But they don't know the calculation that went on behind the scenes about how much they know and all that. Now, hopefully, if this runs for a bunch of time, they'll start to learn what that agent is doing. There will be an actual outer loop here where the regulatory agent can start to see, oh, that company tends to have good drugs and they tend to pick this price level. They can tend to pick the more expensive one because they're willing to make bigger bets, and that could help tune the whole process. Okay, but it's not just an obvious calculation on either side, just given the Fs. Got it? Thank you. Yeah.
Question? Yeah, speaking of this F function you choose in your menu, like so it quantifies what the reward that the profit you're going to make out of the product. But how can you design that in a practical way?
Yeah, so that's a good question. So it doesn't just quantify the reward. Yes, you plug in the observation, you get a reward, but it quantifies the terms as well. Associated with that F is a bunch of terms, like licensing terms. So if you pick that F, you're going to get those licensing terms. Okay, so that goes into the overall utility. That said, that paper just sort of said if and only if it's non-negative super martingales. All right, now if you believe that result, you then go to the papers on non-negative super martingales, which now there are more and more, because those are e-values in statistics. And you say, what are non-negative super martingales look like? And there's various tilting theorems and there's various structures. It has a little calculus of its own. And so what that paper sort of argues is that if you want to work on this topic, you better learn that calculus and learn those objects. Now grab some of them and use them for your purposes. We now do a minimax result, which is to say, if you want to, since you don't know anything here, the minimax thing to do for the designer is to use all possible e-values, okay? But you wouldn't do that in practice. You'd do a subset that are the ones that are more tractable computationally and also just more usable. And then you'd probably, down the line in 10 years, hopefully there'll be theorems that prove how much do you lose by doing the subsets. But it's just kind of the playground that we are now saying if and only if you should be in that playground. And we know what non-negative supermartingales look like. They have a lot of nice structure. So it's not just that you're picking arbitrary functions and arbitrary licensing terms ad hoc. Now it's less ad hoc. Right. That said, then we have some of these follow-up papers where we did this in like federated learning, and then Navasi has done that in data collection kind of things. And it's not necessarily that you start with a non-negative supermarket, goes right down, but this kind of allows you to prove something, even if you didn't do it that way. Yeah.
Yes, so I had a question about this prediction power difference.
Yeah.
So I was very surprised by the last example where you had this census data.
Yeah.
And the predicted value was outside the confidence interval that you get with the predicted.
Okay, you're saying the predictive value is outside of the confidence. I don't know what you mean.
Like you had a.
There was a Monte Carlo ground truth.
Yeah, exactly.
That value, which we assume in real life you wouldn't know, but here because we're pretending we're the supreme being, we know it,
Yeah, so
and we're not covering that. Yes.
you had the ground truth value was covered by your method.
Yeah.
But the input, like the one predicted by the logistic regression, was outside of the confidence interval.
That's correct.
And I was like the logistic regression has to be right on the training data. So somehow, so how can such a thing happen? It's mysterious.
The one the little one that's way off, that's coming from all the unlabeled data.
Okay, I see. Okay.
Yeah. No, that's right. And that's a good question, though. If, on the training data, quote unquote, the labeled data, those need to be gold standard labels, unbiased. All right, and then this method will unbias them. If those are biased, there's nothing we can do. But, now you would want to sort of study how much bias can you tolerate and so on and so forth. So therefore, I think statisticians are paying attention to this probably more than the science people are, because they can now prove some more theorems on loosening some of that. But I'm happy to, in the protein domain, I trust the people in the lab. They got the crystal structure. And I'm happy to build a classifier on that and use that to correct my other thing. And I think in lots of science problems, I'm happy. But in general, I wouldn't be happy, and that would be a thing to investigate. Claire. Oh, sorry.
If I look at your airlines example,
Yeah.
now different people pay different prices,
Yeah.
and this raises a controversy in terms of evaluating people's contribution, individual contribution to global warming. Some people say if 300 people go on an airplane, each of them contributes a 1/300 fraction, and others say proportional to the price they paid. And depending on your viewpoint, you can say rich people contribute a lot to global warming or not that much more than others. How should you compute people's individual contribution to global warming?
Let's get a glass of wine or maybe even a whole bottle and discuss that, because it's really hard. But this is what a lot of economists talk about. And these are the big challenges. I'm not going to answer your question, just to say. But there is, there's a whole literature on fair division. And there's a whole list on public goods and on insurance. And all of those concepts need to come into play to discussing those issues. We can't just say that here's a little algorithm that will do it. Okay, all those issues come into play. All right, but at least as a first step here, it was good to fill the airline because people did get to go from place A to place B. They were not happy. They complained about they were last in line and they didn't like the deal. But and the airlines were viable. In the 80s, they were about ready to die. There wouldn't be airlines. Okay, and now you say, well, the fact that there are airlines is bad because that causes global warming, and that's another externality around all of this that one has got to think about in the overall context of people's need to occasionally get from place A to place B, and who should pay for that when it actually has externalities and all that. But I'm personally going to spend the next 10, 15 years of my career doing economics-related things, always bringing in statistics and machine learning. But I hope to be able to say intelligent things about that eventually. I do think there are people in the world who do know how to talk about fair division and all that. But yeah, there's just the naivete, a breathtaking naivete of like the newspapers and a lot of people who talk about these things. It's just that the bad people are doing bad things. Let's make them not do bad things. And then if you say, well, no, that can't work. It's not, then you're viewed as, I don't know, a right winger or something, which I'm definitely not. So it's really, it's going to be an interesting challenge to liberate a decent dialogue here Even carbon tax, which I'm sure you know a fair amount about, that's been hugely controversial. It shouldn't be. It's like a first step to do other things. And just market mechanisms in general. I mean, I'm now moving to France, and I'm aware that in the US I could say market mechanisms when people say, yeah, that's great. Over in France, I say that, and they say, well, that's destroying the world, you idiot. And so I got to be a little careful here. But I think of it as like, the engineering field. Suppose that you were doing mechanical engineering 200 years ago, and you're saying, I'm going to write down Newton's equations, and I'll use gravity, as a force. And someone said, you shouldn't use gravity. Gravity is a terrible thing. It kills hundreds of thousands of people every year. Because it does, right? People fall and they die. Gravity is a terrible thing. You should not use it in your engineering field. And I say, okay, gosh, all right, I'll use pulleys and I'll use all kinds of, I could develop a mechanical engineering that didn't use gravity, right? It would be a terrible mechanical engineering, but I could do it. And the whole point of, obviously, it's a silly example, but the whole point is it's a force. And if you ignore it, it'll be worse. So don't ignore it, but then regulate around it. Don't regulate in spite of it or in place of it.
So,
Yeah.
Now that you have read La Fond-Artiman, I was trying to
Yeah.
to my terminology as an economist. So,
Yeah.
in your paper, basically, what you did so far is to characterize the implementable contracts, basically. So you haven't solved
Implementable in the sense of incentive compatibility.
Yeah, so you
Yeah.
haven't solved the principal's problem yet.
We didn't solve it in the terms we give you a playground for the principal to play in.
Okay, so you know which mathematical objects you should use
Yes.
to optimize that for.
Yes, and I think of that as progress, but you're absolutely right. That's one first step on the way to a real design like a mechanical engineer.
But then did you solve in some simple problem the optimization problem?
In the Minimax sense, we solved the optimization problem. But again, this is first steps, first baby steps. But yeah, it's like a mechanical engineer knowing that here's the right ODEs to work with.
Okay, so maybe it's time to thanks again, Mike.
Thank you.